Very good morning to all of you. Today we are going to start our next topic, that is solenoid. When a long insulated wire is tightly wound in the shape of spring with closely turned that lies side by side, we get a solenoid. Generally, a solenoid is made by winding wire over a non-conducting cylindrical tube. A solenoid differs from a circular coil in that the length of solenoid is much greater than diameter. When a current enters a solenoid at one end, it passes through each turn before coming out the other end. Each turn produces its magnetic field. Actually, a current carrying solenoids behave like a bar magnet. Okay, the the magnetic field inside a long current carrying solenoid is nearly uniform and is parallel to the axis of solenoid. This is the figure when electricity or electric conducting substance pass through the solenoid. Now, our next topic is electromagnet. An iron nail or bolt. What is bolt? The bigger form of iron nail will not attract iron and steel object solenoid by taking an example of solenoid. Okay, firstly we perform an activity. Okay, now wind a solenoid directly over an iron bolt or nail using 5 or 8 feet of thick enameled copper wire, or we can say that insulated wire. The enamel coating act as a insulator. Okay, and place a battery switch. Okay, now close the switch. The bolt attract iron and steel object. A magnet formed temporarily due to magnetic field of a current is called electromagnet. Now, properties of electromagnets are, unlike a permanent magnet, the electromagnet's magnetism is not permanent. Okay, the electromagnet has pole at its ends. However, the end at which poles appear is not fixed. The poles get interchanged when the direction of current through the solenoid is changed. The iron used in nails, bolts, etc. is soft magnetic material. It is also soft iron. Such a magnetic become magnetized in a magnetic field, but it loses its magnetism once its field is removed. Now, our next topic is a magnetic field exerts a force on a current carrying conductor. We have seen that an electric current produces a magnetic field which exerts force on a magnet placed near it. Now we are going to perform an activity. Connect the end of a small thick aluminum or copper wire to long wire thin wires. Okay, use these wires to hang the aluminum wire from a support. Okay, now connect the wires to a battery and switch as shown in figure 5.10a. Now place a horseshoe magnet as shown. The aluminum wire should swing freely between the poles. Turn on the switch to pass a current. The aluminum wire will move, showing that magnetic field exerts a force on it. Note the direction in which the wire moves. Turn the magnetic upside down. Okay, change the direction of the magnetic field. Now, when a current is passed through the wire moves in the opposite direction. The direction in which the wire moves also changes if you change the direction of the current by the interchanging the connection to the battery. You know that current flows from the positive to the negative terminal of the battery. Also, the direction of the field of a magnet is from north to south pole. So, based on your observation of this activity, you can say that the following are true for the carrying conductor placed in the magnetic field. A current carrying conductor experience a force in the magnetic field The direction of a force depends on the direction of the magnetic field and is perpendicular to it. The direction of the force depends on the direction of the current is perpendicular to it. This is all for the day. Thank you, class.